Hey CIS, I miss you. I hope you had a good couple of days off, but we are ready for conditional probability. This is your last packet. You already have this, and the answer key is connected to the back of it. I think it is pink, if I remember right. So in this screencast, we are going to talk about conditional probability. To write conditional probability, we're going to have a P, yeah, don't judge my writing, of event E, and then we're going to have this vertical line that states given that some event has already happened. So this part is already known, and this is our event happening after the C has happened. So this is how it's going to look like for conditional probability. If a fair dice is rolled, the probability of rolling 5 is 1 out of 6. However, if I'm told that it's an odd number, it reduces our total chances. So instead, we have, let's see, one piece here. Oh my goodness. Found it. So we know that instead of 6 outcomes, we now only have 3 outcomes. 5 is one of those options. So given that it's an odd number, we would say the probability of 5, given that it is odd, equals, instead of 1 out of 6, we have 1 out of 3. So this reduces our total number of events that can occur. All right, so a lot of the conditional probabilities we have are going to be given from a table like this that you see on your screen. If one of the 55 books is randomly chosen for reading, find the probability that it will be hardcover. Well, hardcover totals is 30. We have 30 out of 55 as a hardcover. Now, continuing with this, if we find the probability the book is fiction, given that it's hardcover, we say the probability, pardon me, probability of fiction given hardcover. Looking here, we have 30 hardcovers. So we aren't going to be out of 55, we're going to be out of 30. And we have 12 that are fiction. So we have 12 out of 30. We need to reduce that. Both of them can be divided by 3. So we would have 4/10. Actually, both can be divided by 6. So we have 2/5 as my final answer. This is conditional probability. We have a condition so that we don't have to look at our full value of totals. Here is the conditional probability formula. P given event, probability of an event given F has happened is the number of outcomes for both E and F out of the number of possible with F. So that's the intersection divided by total of F. That from that last table, 12 is the intersection of hardcover and fiction out of the hardcover total. So that's where those numbers would come from. Alrighty, moving on, if we have a dice again, the example 2 fair dice are rolled, find the probability that the sum is 8, given that both dice show the same number. Well, if both dice show the same number, we have probability that the sum equals 8, given that we have doubles. So I'm just going to say D for doubles. Well, there's only 6 doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So how many of them add up to 8? 4, 4. So we have a probability of 1/6 once we know that we have only looking at the doubles, which one adds up to 8. So you don't have to look at all of them that add up to 8, just the doubles. So the conditional probability is a way to lessen that value of total. Sometimes we don't know the exact values of the intersection, and so we can still compute conditional probabilities even though. So we have E and F out of the total number divided by F out of the total number. So that can reduce down to this. The alternative formula, is kind of behind my face, I think. So let's move that up just a tiny bit. We have probability of P and E divided by F, which can simplify down to the intersection divided by F total. Kind of the same thing. Suppose a poll of local voters indicates that 42% of a property tax increase to support local schools. 60% favor adding horse racing as a means to create state revenue, and 15% favor both. So I would start with my Venn diagram on this. With my Venn diagram, I've got property tax, I've got horse races, and I've got 15% in the middle, and it says 42. Well, that includes the 15. So how many people only do the property taxes? Oops. 42 minus 15 is 27%. Here we have 60%. Again, how many only are for the horse racing? That would be 45%. So in this case, we've got 87% of the people that wanted one of them at least. So that means we've got 13% that are not included in here. And I like to just kind of keep that out here. So if a voter is in favor of property tax, so that's over here, that entire circle has a total of 42%. Because we know that it has to be inside the property tax circle. What is the probability that they're also in favor of the horse? Well, that is the 15%. So we've got 15% out of 42%. If I quick divide that, we get 37.5, no, I lied, 35.7%. And that would be my final answer. 15 of the 42% are in favor of both. So this is conditional probability. Multiplication rule, again, as long as they interact, if they overlap, that is the in-between part, that is the intersection that we talked about. To find the intersection, this right here is the formula. It's the probability of F times E conditional of F. So this is just solving the previous formula we had for the intersection. If I multiply both sides by the number of F, that's how we're getting our current formula, which is right here. Okay, so the intersection equals the condition times the total of F. So this is the same formula. I'm not asking you to memorize this, just solved for a different variable. Two cards are drawn from a deck without replacement. What is the probability both cards are aces? So in the first piece here, we have they're not replaced. So we start with 52 cards, and then after that we're going to go down to 51. We've already done a little bit of this. So the first one, there are 4 aces out of 52. The event of the second card being an ace, if that first one was pulled, there's only 3 left. But now this time there's only 51 cards left. So to find the total here, we've got 4 out of 52 times 3 out of 51. Both of these can reduce, so that's our final answer. And again, you should reduce first. It's going to save you a lot of time in the end. So we've got what meteorologists have difficulties predicting weather, especially rain, in a short time period. They appear to have more accurate predicting when it's not raining. The following table gives outcomes for 1,000 1-hour time frames. So rain forecasted, no rain forecast. So this is how the forecast rain, when it did rain, forecast no rain, when it didn't rain, and then here's your totals. What is the probability that rain was forecasted and it rained? So we're talking about the what's the given? We know that rain is being forecast. So the probability of rain forecast is P of F out of, we have 220 for the forecasted out of a total 1,000. So forecast correct rain would be rain out of forecasted rain, 62 out of 220. So those are your two questions in the beginning. Okay. The probability that no rain is being forecasted is 780 out of forecasting no rain out of our total. And again, how many times did we make that prediction? Our prediction was 762 forecasted no rain, and it didn't rain out of that 780. So that's where we got this one. Alrighty. Notice this information can be taken directly from that table. I showed you how I did that in the 3 previous slides. Good luck on the first half. I will do one more video for the second half of this worksheet. Please email me with questions as you have them. I will start with some questions in my second video. Have a good day and stay healthy.